E-bikes have absolutely revolutionized urban transport, right? I mean, they're everywhere. But that rapid adoption has triggered a parallel crisis that we urgently need to understand. So, in this explainer, we're going to dive deep and uncover the gripping forensic science behind the global surge in micromobility fires. Today, we're going to look strictly at the engineering and electrochemical facts to see exactly why these catastrophic lithium-ion battery fires are happening, and more importantly, we'll see how the rigorous UL 2271 safety standard is fighting back against those highly dangerous gray market knockoffs. To really grasp the scale of this issue, we just need to look at this number, 108. That shocking number represents the e-bike lithium-ion battery fires attributed by the FDNY in New York City in 2023 alone. And to be clear, we aren't talking about small sparks here. We are talking about explosive, incredibly fast-moving residential fires that have, tragically, resulted in numerous fatalities. You see, the shift from heavy lead-acid batteries to energy-dense lithium-ion was completely necessary to make e-bikes lightweight and practical, but it brought extreme chemical volatility right into our living spaces. So why exactly is this happening? Well, we have to look at the secondary market. In our real-world case study of New York City, food delivery couriers who need high continuous discharge rates to work all day turn to non-certified packs built by informal technicians just to save some money. They'd charge these overcapacity batteries using incompatible chargers in clustered, completely unventilated apartment hallways. And when one of those batteries failed, it failed violently, often right in the middle of the night while the building's residents were fast asleep. Let's put on our investigator hats for a second and zoom way into the microscopic scene of the crime to define our core threat: thermal runaway. This is the exact mechanism causing these explosions. Basically, it's a catastrophic, self-sustaining exothermic chain reaction. Once this reaction kicks off, the battery essentially feeds on its own heat. That causes a rapid, incredibly localized spike in temperature and pressure, which eventually vaporizes the liquid electrolytes inside and violently vents highly flammable gases. This right here brilliantly illustrates the terrifying ticking clock physics of how a single failing cell cascades into a violent jet flame. It fundamentally begins at the SEI layer, the solid electrolyte interface. If the cell is overcharged and internal temps cross 120 degrees Celsius, that SEI layer breaks down exothermically. Suddenly, the highly reactive anode is exposed directly to the electrolyte. By the time temperatures hit 200 degrees, the thin polymer separator inside simply melts away, causing a massive internal short circuit. Finally, the metal oxide cathode collapses, it releases oxygen, and that instantly mixes with the vaporized electrolyte, igniting into a full-blown fire. Okay, let's nerd out for just a second, because when thermodynamics take over in uncertified batteries, the lack of thermal management means the heat simply cannot escape, leading to an uncontrollable acceleration. Looking at the energy balance equation from the research, the absolutely critical variable here is Q loss, which is the heat dissipated to the surrounding environment. In densely packed, cheap knockoff batteries that have zero thermal management built in, Q loss is essentially zero. That forces the temperature to skyrocket exponentially until the cell physically ruptures. But wait, it actually gets worse. Beyond the intense fire itself, we have to examine the highly toxic chemical cocktail released into the air when high-capacity NMC batteries vent. When thermal runaway happens, the flame is only half the threat. Studies show that advanced lithium-ion cells release substantially greater volumes of lethal off-gases. We are talking about carbon monoxide, hydrogen fluoride, and hydrogen cyanide, which honestly is why a battery fire in a confined space, like an apartment hallway, is so profoundly dangerous, even before the flames manage to spread to the building structure. All right, let's move into Section 1, the digital brain, also known as battery management systems. Now, what's really fascinating here is the stark contrast in the engineering. It's essentially the difference between a vigilant security guard monitoring every single cell versus a cheap system that literally sleeps through critical imbalances. A UL 2271 certified pack utilizes active multi-point cell balancing. It's constantly watching every parallel group individually, and if even one group gets stressed, it immediately shuts the system down. Knockoffs, on the other hand, use substandard boards with passive, single-point monitoring. They only look at the total aggregate voltage of the entire pack. And because those knockoffs only read that total aggregate voltage, an incredibly dangerous situation can unfold right under your nose. A technician might plug in a battery and read a perfectly normal 54.6 volts on the output. But internally, one cell group might be dangerously overcharged while another is severely depleted. These hidden electrical imbalances cause microscopic dendrites, these tiny tree-like structures of lithium metal, to grow like little spears inside the cell during overcharging. Eventually, those dendrites literally pierce the separator, inevitably causing a massive short circuit. Let's dive into Section 2,
the expert comparison matrix, pitting UL 2271 against the knockoffs.
The data here is wild. A certified pack survives mechanical drops and isolates electrical faults in literally microseconds. Check out the cell isolation metrics. Certified packs use specialized high-temperature potting compounds in precise physical spacing to stop heat from jumping from one cell to the next. Uncertified packs, they literally jam the cells together with hot glue. Furthermore, certified packs are strictly verified to survive a 2-meter drop, but knockoffs are usually housed in brittle ABS plastic. So if a rider drops their bike off a curb, that brittle casing shatters, it crushes the internal cylinders and triggers an immediate internal short. Which brings us to Section 3, the energy versus stability paradox. Engineers face a massive dilemma when trying to design these systems, balancing riding range against absolute safety. Here is the ultimate trade-off. High-performance NMC, or nickel-manganese-cobalt batteries, give e-bikes that incredibly light form factor and great range, but thermal runaway can start at just 150 degrees Celsius. They require pristine engineering. On the flip side, LFP, lithium iron phosphate, is incredibly stable. It doesn't release oxygen when it fails and won't hit thermal runaway until over 270 degrees. It won't explode, but it's vastly heavier and basically turns your bike into an anchor. If you want a lightweight bike, you have to use NMC, which means you absolutely 100% must have those stringent UL 2271 certified protections. Let's shift from the chemistry lab out into the city streets with Section 4, Ecosystems and Real-World Risks. Out in the real world, the industry has split into two completely diverging philosophies. On one hand, you have proprietary chargers that verify battery health. Tier 1 brands like Bosch and Shimano operate what we call walled gardens. Their chargers actually use a cryptographic handshake via a CAN bus protocol to verify the exact health of the battery before allowing a single drop of current to flow. Conversely, in open battery swapping networks like those booming in Southeast Asia, having dozens of high-capacity batteries charging right next to each other risks a massive cascading failure. So, to compensate, they actually have to engineer individual steel-reinforced cooling chambers just in case one battery goes into thermal runaway. Finally, let's look ahead to Section 5, the future horizon, and how we're engineering out the risk entirely. This right here is our technological roadmap out of the epidemic. We're moving from strict regulations today to self-extinguishing polymers soon, and eventually to non-flammable solid-state batteries that suppress those deadly dendrites entirely. Right now, aggressive legislative enforcement of UL 2027 is our best absolute first line of defense. But looking just over the horizon, researchers are developing flame-retardant polymer electrolytes with a self-extinguishing time of less than 6 seconds. And by the end of the decade, we hope to see the holy grail commercialized, solid-state electrolytes. By replacing the volatile liquid inside the battery with a solid ceramic or polymer, we virtually eliminate the risk of thermal runaway while actually doubling the energy density. So, what does this all mean for us? Well, the e-bike battery fire epidemic isn't a failure of the lithium-ion technology itself, but rather a direct consequence of unregulated, cheap manufacturing. Knowing what happens at the microscopic level, we have to leave you with this final vital question. Is your daily commute riding on a rigorously certified standard or a ticking knockoff? Use this knowledge to make informed, safe choices about the technology you bring into your home. Thanks for joining this explainer. Stay safe out there, and we'll catch you next time.